Okay, welcome back. In this section, we will complete the remaining questions from part C, data processing for computer analytics. These questions focus on normalization, normalization method, winning strategies, and feature selection. This, and this. Used in decision support system for legal analytics. Let's continue with question 5. So, explain normalization methods for feature scaling, min-max normalization, z-score normalization, z-score using mean absolute deviation, and decimal scaling. So let's get started with question 5th. Okay, so this transform a value v into a fixed range, usually that is from 0 to 1. So the formula for it is given as this, where we have the current value divided by subtracted minimum value divided by maximum minus minimum into new maximum minus new minimum plus new minimum. Okay. When to use this? When we know bounds, when we want consistent interpretation such as risk scores between 0 and 1. This method is common in image and text vector scaling. Second is z-score normalization, in which the mean is 0, standard deviation is 1, and the formula for calculating it is this. When to use this is when outliers exist, when we want standardized comparisons across attributes. In legal analytics, incidents to durations or delays often have outliers, making z-score very useful. Now, third one is z-score using mean absolute deviation. This is more robust alternative to normal z-score. Formula for this is given here. When to use this is when extreme outliers exist, fraud cases and monetary losses often produce heavy tail distributions. MAD based scaling reduces the impact of massive values like rupees 10 crore for fraud cases. Now, moving on to decimal scaling, we divide values by power of 10 until the maximum absolute values becomes less than 1. If max value is 215, we divide it by 1000 to make it 0.215. If we have this, we divide it by 1000 to make it 0.215. Okay. When to use this is simple. It is simple and fast processing, rare in modern machine learning, but still useful in basic DSS tools. Moving on to the next question 6, which is binning case sensitivity. Scores are given as this: partition into equal frequency bin, equal width bins, and clustering based bins. So let's get started. Question 6. Okay, so we are given with the following data. Total values are 12, minimum is 5, maximum is 215. Okay, so we apply 3 types of binning. Equal frequency binning. Okay, so bin 1, we divide them into 4 values which has low severity, and 15 to 55 it has medium severity, and 72 to 215 it has high severity. This approach ensures each bin has balanced workload, useful in triad systems. Second is equal width bins. So range is given as 210, bins are 3, width will come out to be 210 divided by 3 equal to 70. Bin 1 will be from 5 to 75, which is crowded, this becomes overcrowded. Bin 2 is 75 to 145, which contains only one value. Bin 3 is 145 to 215, which is 204 and 215. The insight we get from this equal width binning is distorted by outliers such as 204 and 215. Legal datasets often contain extreme values, making equal widths less reliable. Third is clustering based bins. So clustering finds natural severity groups. Cluster 1, these are petty crimes. Cluster 2, it is moderate crimes, and cluster 3 is heinous crimes. So this approach creates bins that reflect real legal severity boundaries rather than artificially forcing bins. So implications for section mapping thresholds are: equal frequency ensures workload is balanced and across officers. Clustering creates realistic severity levels, separating ultra high sensitivity severity cases independently. Equal width should be avoided when extreme outliers exist. Moving on to the question 7, what we have is feature selection for section mapping. Summarize with a flow chart the techniques for choosing attributes used by DSS, forward selection, backward elimination, and hybrid method. Let's move on to the question 7, which is okay. So, in DSS, the goal is to select the best attributes such as keywords, location, company metadata to predict the appropriate IPC section. So, um, our PDF, our screen provides a flowchart with these techniques. I have written the mermaid form of this. We can just put this in mermaid.js and get the flowchart. So first is forward selection, second is backward elimination, and third is hybrid or stepwise. Let's start with forward selection. We start with an empty uh, feature set, add features one at a time. After adding each feature, check if model accuracy improves, and stop when adding more features does not help. When to use it? When the number of possible features is large, when training cost is low. Second is backward elimination. So it starts with all the features, remove the least useful features from the first, evaluate accuracy, continue removing features until accuracy begins to drop. When to use this? When we know the dataset has many irrelevant or noisy attributes. So third is hybrid method. This combines both forward and backward strategies. Process for this is add the best performing features, recheck older features to see if any became redundant, remove those redundant features, repeat until a stopping rule is met. Benefits are avoiding the nesting effect, produce a more optimal feature subset, useful when relationships between features changes dynamically. So we have covered all the three caution which are last from this test paper. Hope you find this informative. We'll see you next time. Have a great day.